Hello friends, welcome you all to the 13th lecture on function analysis and its applications. In this lecture, we will discuss on bounded linear transformations and equivalent norms with examples. Following are the contents of today's lecture. Bounded linear transformation with examples, equivalent norms with example. Bounded linear transformation. Let X and Y be two normed linear spaces over the same field of scalars. A linear transformation T such that X to Y is said to be a bounded if there exists a positive real number K such that norm Tx less or equal to K norm X for all X belonging to X. Okay, if satisfies this condition, then we say that T is a bounded linear transformation. For example, let X is an element of L infinity and define Tx is equal to Xn upon N. Then T is a bounded linear transformation such that L infinity to L infinity. Explanation. First we prove T is linear. Since Xn upon N belonging to L infinity, for any X, that is sequence Xn belonging to L infinity, we have the transformation T such that L infinity to L infinity. Suppose X is equal to Xn and Y is equal to Yn, both are the elements of L infinity, and A be any scalar, then Tx plus Y. Okay, here Tx defined Xn upon N, so we can write Tx plus Y is equal to Xn plus Yn upon N. That is Xn upon N plus Yn upon N. That is, as per the statement, we can write this as Tx and this one as Ty. Okay, and with scalar multiplication of vector x, that is T of Ax equal to Axn upon N. That is A into Xn upon N. Xn upon N can be written as Tx. That is here Atx. Hence, T is linear transformation on L infinity. Now, we have to prove T is bounded. Here mapping T such that L infinity to L infinity. If X is the element of L infinity, then Tx also the element of L infinity. So, we have to check the Tx under infinity norm. That is, Tx under infinity norm can be written as Xn upon N. Under infinity norm, supremum of 1 less or equal to N less than infinity mod Xn upon N as per the definition of L infinity norm. Okay, since N is natural number, then this expression is less or equal to supremum of N lies between 1 to infinity mod Xn. Okay, so this can be written as norm X infinity. Okay, so norm Tx less or equal to norm X. Okay, so it satisfies the condition of bounded linear transformation. This here K is 1. This shows that T is a bounded linear transformation on L infinity. Next example, let L2 be the nonlinear space of square summable sequences of complex numbers. Let alpha is equal to alpha 1, alpha 2 and so on alpha n be a bounded sequence defined mapping T such that L2 to L2 by Tx is equal to T x1, x2 and so on xn dot is equal to alpha x, where alpha is this one and x is this x1, x2 and so on. It is defined alpha 1, x1, alpha 2, x2 and so on alpha n, xn, infinite dimensional. Okay, then T is bounded linear transformation. So how to say this is a bounded linear transformation? Let us prove it. First, we prove T is linear and then bounded. Okay, so first prove T is linear. If xy belonging to L2 and ABB is scalar, then TAX plus BY as per the statement Tx is equal to alpha x, then TAX plus BY can be written as alpha into vector AX plus BY as this. So multiplying alpha AX, alpha BY. So this is A is scalar, B also is scalar given. So A into alpha x plus B into alpha y. So alpha x here, so A into alpha x can be written as A1 x1, A2 x2 and so on, An xn dot. Similarly, plus B alpha y can be written as alpha 1 y1, alpha 2 y2 and so on alpha n yn dot. Multiplying this by A, so A alpha 1 x1, A alpha 2 x2 and so on. And this can be written as B alpha 1 y1, B alpha 2 y2 and so on. Okay, so this is the infinite dimensional two term. So first term can be added with first term of second. Okay, similarly second term of first can be added the second term of second. So this can be written as in one infinite dimensional vector A alpha 1 x1 plus B alpha 1 y1, second term A alpha 2 x2 plus B alpha 2 y2 and so on. Then this can be written as A alpha 1 x1 plus B alpha 1 y1. Similarly, second term A alpha 2 x2, B alpha 2 y2 and so on. So this can be divided in two terms as A alpha 1 x1, A alpha 2 x2, A alpha n xn as one vector plus B alpha 1 y1, B alpha 2 y2 and so on B alpha n yn as another vector. Okay, so here A common, okay, and from this term B common. So we can write A alpha 1 x1, alpha 2 x2 and so on alpha n xn plus B into alpha 1 y1, alpha 2 y2 and so on. So as per the statement alpha 1 x1, alpha 2 x2 and so on alpha n xn can be written as alpha x. So this vector can be written as alpha x, and this vector can be written as alpha y. So alpha x as t x1, x2 and so on xn. So we can write this a t x1, x2 and so on xn dot 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 plus b t y1, y2 and so on yn dot dot dot. So this term can be written as tx and this is ty, that is atx plus bty. So here we have proved tax plus by is equal to atx plus bty. So t is linear operator. Now we prove t is bounded. Square of norm tx can be defined summation n is equal to 1 to infinity mod alpha n xn square. Okay. So by Cauchy-Schwarz inequality, we can write this is summation n is equal to 1 to infinity mod alpha n square and summation n is equal to 1 to infinity mod xn square. This is norm alpha n square and this here norm x square. Okay, taking the square root of both sides and here also alpha is. Okay, so here alpha 1, alpha 2 and so on alpha n, that is alpha be a bounded sequence. Suppose norm alpha bounded by m. So norm tx less or equal to m norm x. Okay. Hence T is a bounded linear transformation on L2. Third example. Consider a Banach space C01 under infinity norm. Assume that the function k such that closed interval 01 cross closed interval 01 to R is continuous. Define the mapping T such that C01 to C01 by Txt equal to 0 to 1 kts kernel into xs ds, where x is the element of C01. Okay. Then T is bounded linear transformation. Now we prove first T is linear. Okay. Let xy belonging to C01 and AB be any scalar. Then Tax plus Byt can be written as integral 0 to 1 kts axs plus bys ds as per the statement, equal to integral 0 to 1 kts a into xs plus integral 0 to 1 kts into bys ds. A is scalar, B also is scalar, so we can write the outside the integral. So we can write this and this one 0 to 1 kts xs ds. This is a tx and this one b ty. Okay, so tax plus by equal to atx plus bty. This shows that T is a linear transformation. Now we prove T is bounded. Since k is continuous, it follows that k is bounded on closed interval 0 1 cross closed interval 0 1 and thus mod kts less or equal to m because k is continuous, that is bounded. Suppose it is bounded by positive number m. Also, since x belonging to C01, it follows that mod xs equal to supremum of s belonging to closed interval 0 1 mod xs, that is infinity norm of x. Okay, here defined mapping T such that C01 to C01. So x belonging to C01 with infinity norm. So we have mod xs can be written as s belonging to closed interval 0 to 1 mod xs. And this, as per the statement, we can write x under norm infinity. So from equation 1 and 2, we get Tx under the infinity norm equal to supremum of modulus Tx. Okay. Why? Because here mapping T C01 to C01. So Tx is the element of C01 and here norm defined infinity norm. So under the infinity norm, Tx is equal to supremum of modulus Txt. And putting the value of Tx, that is integral 0 to 1, so Kts into Xs ds. Okay, this is the modulus. So we know that mod Kts kernel less or equal to m from equation 1. Okay. So we can write this is bounded by m here and this is x s ds. So taking the supremum value with s belonging to 0 to 1. Okay, that is norm x infinity ds. So this is scalar. So we can write integral 0 to 1 ds, that is 1. So we have m norm x. Okay. So we conclude that norm Tx less or equal to m norm x. Hence T is bounded linear operator on C01. Open sphere or open ball. Let X with norm be a non-linear space. For r greater than 0 and a belonging to x, the set SRA equal to x, where x is the element of x and defined norm x minus a less than r. Or it can be written as SRA equal to x belonging to x with metric dxa less than r. If satisfies this condition, so we can call it an open sphere or open ball with center at A and radius r. Closed sphere or closed ball. As like same definition, here x be nonlinear space with r greater than 0, that is positive, and a is the element of x, then SRA for closed sphere, here notation this. X is the element of x and norm x minus a less or equal to r. In open ball, here less than r, and closed ball, here less or equal to. Okay. Then closed sphere or closed ball can be defined SRA such that x belonging to x such that dxa less or equal to r or dxa, that is norm of x minus a less or equal to r. Noting point, if r is equal to 1 and a is equal to 0, open ball and closed sphere are known as open unit sphere or open unit ball, and closed unit sphere or closed unit ball respectively. Moreover, x belonging to capital X such that norm x is equal to 1 is called the boundary or surface of the unit sphere. The distance of an element x belonging to x from the subset M of x is defined by infimum of norm x minus y for all y belonging to M, and it is denoted by dxm. Thus, dxm is equal to infimum of y belonging to M. Y is the element of M and x is the element of x. Okay. Then, as like this is the vector x and M is the subset and any point, suppose here X, and Y is the element of M. Then the distance between X and the subset M. It is defined in infimum of norm X minus Y. Third, distance between two subsets M and N of X is defined by infimum of norm X minus Y for all X belonging to M and Y belonging to N, and denoted by DMN, that is DMN equal to infimum of X belonging to M and Y belonging to N norm X minus Y. That is, suppose here X is the set and two subsets M and N. Here X is the element of M and Y is the element of N. Then the distance between the two subsets M and N defined by this. Diameter of the subset M of X defined by the supremum of norm X minus Y for all XY belonging to M. Then diameter defined supremum XY belonging to M norm X minus Y. Here supremum. Okay. Then delta M is finite. Then M is said to be bounded subset of X. In this case, here suppose this is the X and M is the subset of X. Then any point X and Y. Okay. So supremum value of norm X minus Y is called the diameter of the subset M. Equivalent norm. Let X be a linear space and let norm 1 and norm 2 on X, then the two norms are said to be equivalent on X if they induce equivalent matrices on X, that is, if they induce the same topology on X. This is denoted by norm 1 equivalent notation, norm 2. Thus, two norms 1 and 2 are equivalent if and only if any open ball in norm 1 contains an open ball in norm 2 and vice versa. 1 in 2 and 2 in 1. Okay. And this is equivalent to saying that for a sequence Xn in X, the converges Xn to X in norm 1 implies converges in norm 2 and vice versa. Okay. Theorem. Let X be linear space and let norm 1 and norm 2 be two norms defined on X. Then these norms on X are equivalent if and only if there exists positive constant small m and capital M such that M norm x1 less or equal to norm x2 less or equal to M norm x1 for all x belonging to X. Let us prove it. Let the two norm linear space order pair X norm 1 and order pair X norm 2 be called X1 and X2 respectively. Consider mapping T such that X1 to X2 as an operator with domain X1 and range X2 such that Tx is equal to X. So T inverse such that x2 to x1, an operator with domain x2 and range x1, such that Tx is equal to x if and only if T inverse x is equal to x. Okay. Yes, simple. T such that x1 to x2. So mapping from inverse we apply, that is T inverse x2 to x1, and here Tx is equal to x, taking inversion, that is x is equal to T inverse x. Okay, so we have this. The identity operator T and T inverse are continuous. Since identity operators are linear, therefore the continuity of T and T inverse implies boundedness of these operators. By the boundedness of T, there exists m greater than 0, such that norm T x2 less or equal to m norm x1. Okay, T such that x1 to x2 and this, and Tx is equal to x. So T is bounded linear transformation because this is the continuous. Okay, so we can write Tx2 less or equal to m norm x1, because mapping T such that x1 to x2. Okay, so Tx2 bounded by m norm x1, this one. Okay, and here Tx is equal to x. So putting the value of Tx is equal to x, that is norm x2 less or equal to m norm x1. Okay, and the boundedness of T inverse, let k greater than 0, that is positive, such that T inverse x under 1 norm less or equal to k x under 2 norm. Why? Because here T inverse x2 to x1. So T inverse x bounded by the norm x2. So we have here T inverse x1 less or equal to k norm x2. Again we have T inverse x is equal to x, that is norm x1 less or equal to k norm x2 for all x belonging to x. Taking k is equal to 1 by m, okay, then m norm x1 less or equal to norm x2, okay, and from 1 norm x2 less or equal to m norm x1. So from 1 and 2 with k is equal to 1 by m, we have m norm x1 less or equal to norm x2 less or equal to capital M norm x1. We have proved. Now we have to prove if this condition is satisfied, then norm 1 and norm 2 are equivalent. Conversely, if the given condition holds, then norm x2 less or equal to m norm x1. Okay, so norm x1 less or equal to 1 upon m norm x2. So norm of Tx less or equal to m norm x1, and from here T inverse x1 less or equal to k norm x2. So Tx and T inverse x bounded. So here we have proved also if we have this condition, then Tx and T inverse x bounded. Okay. Now continuity of T implies that any open ball of x2 contains an open ball x1, while continuity T inverse states that any open ball of x1 contains an open ball of x2. Hence, norm x1 and norm x2 are equivalent. For example, the norm 1, norm 2 and norm infinity are equivalent norms on Fn, where F is a set of real number or complex number. Let x is equal to n tuples of x1, x2 and so on xn belonging to Fn. Then norm x1 defined summation I is equal to 1 to n mod xi, and norm 2 defined summation I is equal to 1 to n mod xi square whole power 1 by 2. Norm x infinity defined maximum of mod xi where I lies between 1 to n. As per the definition, we have defined here norm 1, 2 and infinity. Now we have norm infinity max of mod xi. Okay. So here mod xi, suppose each member of n tuples x1, x2 and so on as maximum number. So maximum numbers added n time. So we have n maximum of mod xi, that is norm x infinity less or equal to n max of mod xi. This gives that norm x infinity less or equal to norm x1. Okay, this is norm x1 and n into norm infinity. Okay, so we have this equation 1. So 1 and infinity are equivalent. Further, norm x2 summation I is equal to 1 to n mod xi square whole power 1 by 2. Okay, so this is less or equal to summation I is equal to 1 to n mod xi, because we have the inequality if a b greater or equal to 0. Here modulus value, that is always positive. So if a b greater or equal to 0, then a plus b power p less or equal to a to the power p plus b to the power p if p lies between 0 to 1. Okay, so we can write this is less or equal to summation I is equal to 1 to n mod xi. So mod xi can be written as mod xi into 1, that is product of two numbers. Okay, applying the Cauchy-Schwarz inequality, we have summation I is equal to 1 to n mod xi square whole power 1 by 2, summation I is equal to 1 to n mod 1 square whole power 1 by 2. Okay, value of this is under root n, and this is summation I is equal to 1 to n mod xi square whole power 1 by 2 as it is. That is norm x2 less or equal to norm x1 less or equal to under root n norm x2, this one. Thus norm x2 and norm x1 are equivalent norm. In view of the fact that equivalence of norms is an equivalence relation, it follows that the above fact that norm 1, norm 2 and norm infinity are equivalent norms on Fn. Okay. In this lecture, we have discussed the boundary linear transformations and equivalent norms with examples. These are the references we have used in this lecture. Function analysis, Dover publications by George Beckman and Lawrence Naressi. Introductory function analysis with applications, John Whaley, written by Erwin Krejcik. Third, function analysis, New Age International Publisher by B.V. Lemieux. And function analysis, Tata McGraw-Hill by Carter-Rudin. Thank you.